All right, so have you ever stopped and thought, like really thought, about how strange reality actually is? I mean, like truly bizarre.
Yeah.
I find myself going down these rabbit holes every time I even think about quantum mechanics.
Yeah.
So that's what we're diving into today. This article we're looking at digs into why quantum mechanics is such a brain twister, even for the people who, basically live and breathe physics.
For sure.
Get ready to explore why quantum mechanics is like trying to catch a lightning bug in a hurricane, and what the heck math has to do with it all.
I think, one of the most fascinating things about learning about quantum mechanics is that it's not just like adding more information to it's like rewiring, literally rewiring how you see the world.
That's so true. And this article really hits on that right away with this story about this student at CERN, Gabriele Carcassi. He was like, I need to understand quantum mechanics, like it was an obsession. So what'd he do? Read 30 books on the subject and picked the brain of every physicist he could find.
Right. And here's the thing. As impressive as that is, his experience isn't unique. I think it gets at something really fundamental about quantum mechanics. It just constantly challenges our intuition, right? Because you and I, we experience the world through this lens of classical mechanics, the things we can see, the things we can touch, the things we can measure directly. But quantum mechanics, it's operating on a scale that's so small, so fundamentally different from our everyday experience, that even if we could wrap our heads around all the equations, our brains kind of struggle to really grasp it.
And that's a great point, because this article really stresses how important math is to even starting to understand quantum mechanics. It's not even just using math for calculations. It's like math is the language of this
I
stuff.
think that's a really good point. I mean, it's like, yeah, sure, you can translate a poem word for word from one language to another, but are you really going to feel it? Are you really going to understand it? To really get it, you have to understand the nuances of the language it was written in. It's like, imagine trying to, I don't know, read Shakespeare in the original Klingon.
Okay, that's a good analogy.
Right. You'd need a deep understanding of Klingon grammar, of Klingon culture, not just a dictionary, right?
For sure.
And quantum mechanics, it's kind of similar. Math, it's the key. You got to unlock those secrets.
Okay, so you're telling me I need to learn Klingon and advanced math to wrap my head around quantum mechanics.
Pretty much.
This is getting out of hand. But seriously, this whole language idea, it really highlights just how different classical and quantum mechanics are.
Absolutely.
Tell me more.
Okay, so think about it like this. With classical mechanics, you want to understand how a ball moves. You track it like a little red dot, right? You trace its path. You can predict where it's going to go. Pretty straightforward. But then we zoom into the quantum world. And suddenly, our nice, neat red dot, it's flickering, it's in and out of existence, and its position. Forget about knowing for sure. Now it's all about probability, not certainty. That's where that famous uncertainty principle comes into play, and it makes things, a tad more complex.
Oh yeah, just a tad. And on that note, the article dives into how even our most reliable mathematical tools, something like calculus, which is a powerhouse in so many ways, even that can feel a little, well, clunky when we're trying to use it in the quantum world.
Right.
Like Carcassi, that student we were talking about, he specifically brings up infinesimals, these like infinitely small quantities that calculus relies on, and says those are a real sticking point.
Yeah, that's a really interesting point that he brings up because it speaks to a bigger thing about how we need to constantly be examining and re-examining the tools we use, right? Especially in the face of new realities, because calculus, as we typically use it, it relies on this idea of smooth, continuous change. But the quantum realm, things jump around. They exist in these discrete states. So it's not that calculus is like wrong. It's just that we might need to rethink it, adapt it to really capture that kind of like choppiness, that jumpiness of how quantum phenomena actually behaves.
It's like trying to use a telescope to look at something microscopic.
Yeah.
It's just the wrong tool for that job. So there's one more head scratcher I wanted to throw your way from this article. It hinted at this totally unexpected link between classical mechanics, thermodynamics, and this thing called symplectic structures,
Oh, yeah.
which, I'll be honest, sounds a little intimidating.
Yeah. It's less complicated than it sounds, I promise, but it's good stuff.
Okay, good.
Because think of symplectic structures. Like, okay, imagine the underlying architecture of a building, right?
All right.
You might not see it, but it's what's dictating how the rooms are laid out, how they're connected to each other.
Okay.
It turns out that these structures, these symplectic structures, they underpin both classical and quantum mechanics, which is kind of wild when you think about it. It's like discovering this hidden connection, like we're finding these secret tunnels between what we thought were totally separate buildings.
Well,
Right. And it doesn't stop there. These structures also tie into thermodynamics, which, is all about energy and how it's distributed, how states change within a system. So we have classical mechanics, quantum mechanics, thermodynamics, all interconnected in this really deep way, all united by these underlying structures, kind of like rooms within that building we were talking about.
so, okay, I got to ask, am I getting this right? Are you saying quantum mechanics is less like solving a neat, organized puzzle and more like, I don't know, jazz improvisation?
Maybe. I mean, I think that's a great way to put it, honestly. It's about being comfortable with uncertainty, with probability, and realizing that everything's connected in ways that, frankly, we're only just starting to understand.
This conversation has definitely stretched my brain in ways I didn't see coming. It's a lot to process. But I want to leave you with one last thought, something to ponder. Imagine if something as simple as, I don't know, light reflecting off a window wasn't governed by the laws of classical physics, the ones that are so predictable. What if that light was behaving according to the rules of quantum mechanics? How differently would our world look? That's something to think about. So until next time, keep exploring the universe, the one within you and the one, out there.